this is ADW, and today we are back in our redstone computer, and, well, today we're gonna finally get down to actually doing some programming. Yeah, it's been a while, and I really wanted to get into this as soon as possible, but some stuff's come up, and as usual, I don't have much spare time, so yeah. Anyway, today we're going to be going over a really simple addition program. Now, this program, first of all, let's give a little tutorial, or show off, I guess. Let's go ahead and turn this on, and we can see this computer just go ahead and chunk away at solving this really simple addition problem, which is 5 plus 3, and common one. By the way, something I just like to mention whenever I have stuff like basic addition coming up, and there's our input, which is 8, which is correct. The best things to test a binary adder with, or the best numbers to, are 11 plus 1, this right here, and 5 plus 3. Now the reason for this is that they actually go through all of the different possible inputs for all of the different parts of the adder, those two together. So that basically just makes it so that if there is an error, it will come up if you make one of these, if you do one of these math problems. So anyway, that's about it for showing stuff off. I could do this now. As we can see, the program is off, but now it's about time that we started talking about I/O. And that's the thing that today's video is really going to be about, using the input-output system. Last time we talked about how to do all of the really nice and complicated stuff that we can do with our instruction set, but today we are going to be focusing on using this I/O and integrating what we know with our programs into this. And the reason that we want to start with I/O, even though it's not the simplest part of a computer, is it is the most important thing for us to know. It's a lot easier for us to know, hey, we can just send whatever output is in this register, rather than having to go in and say, okay, I didn't build this computer, so I don't know which register this is, and this register is supposed to have such and such value. In fact, you might not even know if you didn't watch the building series that I did for this computer, or our me, that these in here are in fact our registers, and the stuff over there is our memory. And, oh, by the way, yeah, all the signs on the world that I'm actually doing this on are kind of screwed up, so hopefully it's not going to be too distracting. It's actually kind of interesting sometimes. This is because I switched the versions of this world, but you can actually see like how the computer stores all of the different, what's it called, all the information for the signs. But anyway, I'm getting off track. So where was I? Oh yes, you might not know where the information is stored, so knowing how to use this input-output system is going to help you a lot with debugging, and also if you're making a program, in the end, you're almost always going to want to be using the I/O for something. And because of that, it's the first thing that we're going to be tackling today. So let's start off by talking about how exactly the system that I have got going on here works. So, as you can see, I've actually kind of already gone through stuff, but I think it's about time we explained what stuff is. So these things right here are the main interest of the I/O. This is our B input, and this is our A input. So these inputs are the things that are going to actually, we're actually going to be able to send data into the computer using these things. So yeah, this is the least significant digit over here, and this is the most significant digit. The same applies for the output up there, and that's just the same system. So let's start talking about all these buttons and wires and levers. This lever right here is probably the simplest one, and this one is just turns the computer on or off. I'm pretty sure I've been over that before, and these are both for debugging. I explained in the last video that I actually said that you should probably turn this on if you want. Like, if you want to experiment with stuff, this is a good idea to turn on, but otherwise you're probably not going to want it. For example, in the thing we're going to be doing today, we don't actually need to use debugging, but yeah, so you can pretty much usually ignore that. So up here, we've got a input needed, again, this stupid null stuff, and this right here is just saying that, okay, we've got an input that we need to send into the computer. And these lights over here are actually new since I originally made the computer. By the way, there's a few things on the latest version that were not on the older version that I originally released, and including actually I've actually found a bug in this current version, and I've isolated it, and I'm nearly done with it. I'm pretty sure it's not too big of a deal, but I've been working on this world a lot. I haven't been uploading that much of it because a lot of it was because I was worried about that bug, but I'm starting to get really close to almost definitely being able to solve that. But anyway, so this stuff is new. This tells you which input you need to send information into. Okay, so we've got this nice cool light over here that tells us that we need an input, but where do we need it? So this thing right here tells us that we need an input on our input B and our input A, so we just send those numbers in there. And then we have a submit inputs button that we can just press like that. That light turns off. These lights take a bit longer to turn off. That's just delay and the way the computer works. But as you can see, now our output has been stored up there. And then finally this light right here turns on. And this light is just an indicator to tell us that the program is done. This is activated when we make a stop instruction. So yeah. Now, the last thing I'm going to talk about, I'm actually going to go ahead and turn the computer off. And this right here is a reset all memory. And this light up here is actually corresponding to that. And what this is going to do is, first of all, the registers are automatically going to be cleared whenever the computer turns off. So there's that. And then the other thing is that now, if we press this reset all memory button, you can see that it just reset the output panel up there, and it also resets the rest of the memories. So that's another useful thing that you might want to have up your sleeve. Typically, when you finish a computer, you're going to want to do that, or finish a program, you're going to want to do that. But sometimes you want to keep your memory from time to time, which is why that is an option. It can be a bit of a pain to remember to do it all the time, and it might cause you a few bugs, but for the most part, just doing that and remembering that that's an option for you is a good thing to remember. Anyway, so now that we've talked about all of this stuff, let's move on and start talking about how we can do this using a program and start programming the program that's going to be able to do this. Now, before we actually get into programming our little program that we're going to use to do this addition problem, we're actually going to need to talk about the way that this computer handles I/O. Now, naturally, if you're from my Building a Redstone Computer series, where I explain how this computer works, sorry about my phone, by the way, it's probably going to be going off a lot today. Anyway, so where was I? Oh yes, memory in this. So, the thing about the way that this computer specifically works is that, well, It uses this system called memory mapped I/O. And memory mapped I/O is a way of using inputs and outputs in which you don't exactly have a send to I/O or read from I/O specific command. You probably would have guessed that that would have been one of our single operated instructions, like take something from the I/O to this register. But we've actually done something a little different. The way that this computer works is that it actually treats our I/O over here like it's RAM. Now, what this means is that if we come over here, then whenever let's just say that we have a pointer that points to our I/O, and we're going to be talking about what that is in a bit. But if we have a pointer that points to our I/O, and we want to say read from this input, we would say read from I/O, and we would treat it like it's just an address in memory. Similarly with output, if we want to save something to this specific address, then we would just save it to the output. So now let's talk about how this computer actually handles memory. Now, so far, this is pretty much the only part of the instruction set that I think I didn't cover in the last video, and that is that this computer actually only has 32 bytes of RAM. Now, the reason for this is that, or first of all, I should explain why that's unusual. This is an 8-bit computer, right? So if you remember last time, or over the past few videos, I've been talking about how you can use a pointer to point to a certain address in memory, right? Well, let's say that you have an 8-bit pointer. So in other words, I'm actually directly taking my information from my register and I'm directly putting it into memory. Then there are 256, because that's the maximum number of addresses that you can represent with 8 bits, different addresses that you can save memory to. And if each one of those is 1 byte, by the way, just standard measurements of information, 1 byte is 8 bits, and 1 bit is one on-off wire, like one of these ones in binary. So this across here is 1 byte. So this only has 32 rather than the 256 bytes that you would normally have. And the reason for this is that this actually only uses 5 wires. As you can see, there are actually physically 5 right here to go into memory instead of the usual 8. So what do we do with the other 8, starting with the last 3 bits? Well, when we're using, well, first of all, I should talk about what the 2 bits that are the most significant bits are, because these 5 bits along here actually represent the 5 least significant bits. Bit significance, by the way, is just the way that you would say like least significant digit or most significant bit digit in a decimal system, so like ones place versus tens place. The less significant one of those would be the ones. Just standard information representation notation. Try to say that 10 times fast. Anyway, so what we're going to do with these 2 most significant bits is we're actually going to come over here, and we're going to come into a pretty simple decoder. Now, in this decoder, there are 4 different options, because this 2 bits represents 4 different states. And these 4 different states determine where the rest of the bits go to and what information they represent. So what does this mean? Well, if the number in the 2 most significant digits is 0, then it's going to say, well, if the 2 most significant digits are 0, then the system that I want to use is the computer's memory. So I'm going to just take the value of the 6 least significant bits and send it into the memory over here. Whereas if I was to do 1, 1, it would actually ignore the other bits, and it would use that to access our I/O, and we would have our pointer. Now, just because I want to make sure that the way that this computer works is very clear for you when you're using memory. So we've accounted for the 2 most significant bits and the 5 least significant bits, but that leaves one more extra bit at the end there. And that bit is actually used to determine whether or not we're using, or the memory address that we're accessing is a RAM address or a ROM address. Now, if you want a bit more on memory, I have a kind of basic playlist for that. That's not very good, and I did a while ago. But basically, ROM is the stuff that's like down here, where you should know what RAM or ROM is coming into this. So yeah, why am I even trying to explain that? Anyway, if you do not know what RAM and ROM are, then just let me know. I'm a small enough YouTube channel where I can probably explain it in a comment. So anyway, back to this. So that's what that's used for. If you want to use RAM, you want to make that 6th bit 1, and if you want to use ROM, then you make that 6th bit 0. So anyway, with all that gibberish out of the way, I guess you could say, all we need to do in order to access our memory is make a pointer which has the 2 most significant bits being 1. So how could we do this? How do we instantly get our 2 most significant digits to 1? And one trick that you can actually use that has a few other advantages that we're going to talk about a bit later when we start getting into a bit more complicated programs than the one we're doing today, is that you can just decrement a register and all of a sudden it becomes all ones. Now, like I said earlier, it actually doesn't matter what the other bits are when you're accessing I.O. The way that you determine the different inputs to, or the way that you distinguish between these two inputs is actually the bus that it inputs onto. Whenever we access, whenever we access the input-output system using a pointer to an A register, whenever we point to it using our A register, we're going to get the A input, and whenever we point to it using the B register, then we're going to get our B input. So that's the way that's determined. It doesn't actually involve these different wires here, so yeah. Anyway, back on topic, if we just decrement a register, then we can use that register's pointer to access our I.O. So let's actually stop dilly-dallying and actually start coding this in. So the way that this program starts is just like that. We're going to decrement the first register. So now, all of a sudden, we have a way to access our I.O. So naturally, we're going to use whatever inputs that we receive from the I.O. as our operands. So for our next instruction, we just need to take the pointer of where register 0 is pointing. Sorry, the pointer of register 0. So we just set it to an address that points to the inputs. So now if we just take what it's pointing to, then we can just get the inputs. Now what we're going to do is we're going to use the add function. By the way, this instruction over here, this is single operanded instruction, and 1 here is decrement. I'm pretty sure I went through all of the different instructions in the first video where I went through the instruction set, so yeah. And anyway, this is add, so we're going to want to add what is at register 0 to what is at register 0. So this line right here is going to go ahead and just come in here, and it's going to take the 2 inputs, and it's going to add them together, and it's going to send them to the output. Now, because our A register is both our A input and our output, it actually makes it so it will automatically save to the display up there, and whenever you use an A input ever with the I.O., then it's going to save it to your display. something you might want to keep in mind. But other than that, right now we could care less. All we really want to do is make it so that whatever addition problem we see, it gets displayed on that screen. So now the last thing we want to do is a stop instruction, because we've done everything that we want to. We've added two numbers together, and yeah. So the way you make a stop instruction, again, is it's a single operand instruction with just all ones. So in short, all ones from this bit out. So now that we've got our program done, let's go ahead and just test this program out one more time. Let's just do the 5 plus 3 as per usual. Now, I know we've been over loops, and you might think it might be a bit practical to use a loop here, and it probably is, but for today's video, I'm really just focusing on trying to teach how the I/O system of this computer works so that we can move on with stuff. Again, if you want to actually make a loop yourself, then you can go ahead and try, but we're actually going to be talking about how to do that in the next video. Anyway, so that's our first number that we want to see. 5 plus 3 is 8. So now let's test the other basic program. Turn that off. Actually, we don't even have to reset the memory this time, since it'll just replace what's already in the display. So now, hello? Okay, that was probably just a bug. Okay. Or an inconsistency. Sometimes the timing on when you turn the computer off is a bit annoying. So yeah, see, it worked that time. You can't like quickly turn it on and off, so just keep that in mind. Anyways, so here's our next two numbers, so we should see a 12. Ta-da! You can actually see these pistons up here firing, which is the thing that signifies that the problem's done. But anyway, now let's go ahead and do a slightly more complicated program, like say, could do, well, I probably should have prepared a problem to do here, but let's just do like 7 and whatever number this is, and now I can actually try to calculate it. So that's 1 in the 16s, 1 in the 8s, plus 1 in the 4s, and 1 in the 1s. So 29 is what it should be. And 29 should be, no, it shouldn't be 29, should it? 16, 8, so 20, yeah. Oh, 29 plus 7, of course, yeah, that's more than 32. I was confused a bit for a second. So 29 plus 7, and get rid of the rain. So 29 plus 7 is 36, so that is what we should see. And that should be 1 in 32's place and 1 in the 4's place. So just this light and that light on. So let's see. Yep, perfect, yay. Okay, so everything is working just fine, and yeah. So I hope you guys have enjoyed, and I'll see you guys next time where we're going to be talking about the sample program that I showed off in my first video about this, where, like I said, this is like your sample program, the Fibonacci program to be exact. So yeah, I'll see you guys next time.